like me. She don't give a damn about society. Might be a little rich girl, she might be poor. She might be a married woman that needs a little more. Yeah. She's an outlaw woman, first of a kind. These outlaw women riding high in 79.
Alright, I think I'm ready now. I just had to get my thoughts in order before I started. Hank Williams Jr. is always good at helping me getting my thoughts all lined up. In the first video in this unit, I used some country music. I used some Sturgill Simpson, so I thought I'd keep that theme going for the second video in this unit. And the unit I'm talking about is Unit 2, Industrial Toxicology, and this is for our industrial hygiene class. Let's lost my place. Here we go. Now this is actually the second video for this unit. I have a part 1 video where I introduce industrial toxicology. I made it to I think like 42 minutes. I thought I'm wearing out here, wearing down. Let's go ahead and make part 2. This is part 2. We're going to finish up our initial discussion of industrial toxicology in this video. But in that first video, in part 1, I defined toxicology, industrial toxicology, talked about types and classifications of toxins, talked about asphyxiants, acute and chronic toxicity, systemic toxicity, localized toxicity. We talked about organ-specific toxicity, and I don't think we actually talked about species-specific toxicity in part 1, but I will mention species-specific toxicity today in part 2. We talked about sensitization, desensitization. We've really pretty much covered everything that I want to cover as an introduction to industrial toxicology, but I do want to talk about the dose-response relationship, the effect that dosage has on toxicity, and also want to talk about toxin interactions. Hopefully this video will be 30 minutes or so, just putting the finishing touches on our introduction. Mostly it's going to be terminology that as safety professionals you need to be familiar with. So let's go ahead and jump into it. Dose-response relationship. As the dosage level increases, the toxic effect increases. That's probably the most important relationship we can talk about when we think about the toxicity of a substance. More substance, more toxicity. Again, toxicity of a substance determined by the dosage/concentration level. That's not the only variable involved. That is not the only variable involved. And I'll mention those other variables on the next slide. And I do want to harken back to something I mentioned in part 1 of this discussion of industrial toxicology. Pretty much anything out there can be toxic if the dosage is excessive. In large dosages, pretty much anything can be toxic. Flip side of that is many of the substances that we talk about as safety professionals as being dangerous to workers, like manganese and chromium, those are actually considered nutrients that are necessary to our health at appropriate levels, and also when introduced into the organism appropriately. Chromium in our vitamins, manganese in our vitamins that we ingest, that we take orally, and we're talking about very low dosage levels, that's needed for optimal health according to nutritionists and medical professionals who specialize in nutrition. A little manganese, a little chromium, and I think I mentioned silica in the last video as also having nutrient value. But at high dosages, these things are fatal. At low dosages, it's good, we need them, but at high dosages, and also dependent on how they are introduced into the organism, route of exposure also plays a role as well. And we're going to talk more about route of exposure as it interacts with the size of the dosage or the dose-response relationship. Again, other variables affect this relationship, and I'll mention those on the next slide. But for now, I want to mention another concept, the threshold of effect. The threshold of effect is the concentration threshold where damage to the organism starts to occur. And you're probably thinking, well, where do they get all these numbers from? How do we know what the concentration is when how do we know the point where damage to an organism starts to occur? Laboratory research, epidemiological studies, and so on are the foundation for these threshold concentrations that we talk about. And I'm going to say more about that as we move along. But for now, we know this through research, through many years of research, of studying the effects of different toxins on organisms. Now, the threshold of effect, now that is related to but slightly different than the exposure limits that I've mentioned before and that we're going to talk about in another video. The exposure limits that I'm going to be talking about in the subsequent video, these are exposure limits that have been established for workers in the workplace. The threshold of effect concentration values, this doesn't have anything to do with whether it's in the workplace or outside the workplace. It's just a concentration that is thought to have effects on organisms, whether in or out of the workplace. Threshold of effect is also affected by individual differences. Some people are going to be more tolerant than other people to the effects of certain substances, and environmental conditions. And with these two, I'm kind of getting into the other variables that can affect the toxicity of a substance. Other variables in addition to the size of the dosage or the concentration. Route of exposure plays a role. We know the routes of exposure are ingestion, inhalation, absorption, and subcutaneous, or through the skin. And that subcutaneous exposure can be intradermal, intravenous, or intramuscular. Intravenous, the substance is introduced into our blood directly, into our veins. Intradermal is just in the skin, under the skin. Intramuscular, it's injected into muscle tissue, more of a deep injection. And the subcutaneous route of exposure, probably when we look at some data, I don't want to say probably, it is, when we look at data here in a few minutes, we'll see that subcutaneous type of exposure is most problematic. If it's injected into our system, it's going to take less toxin to have adverse effects on our bodies, on organisms. So route of exposure affects the dose-response relationship. The age of subjects, the sex, the size of the organism that is being exposed to the substance, these also play a role. A large man, 300-pound man, it's going to take more of a substance to affect his function, to affect his health. It's going to take more for a 300-pound man than it would for a 150-pound woman. It's going to take more for a 300-pound man than it would for a 150-pound man. Size, sex, age, these variables also affect the effective dosage. The health of the exposed organism. Are there pre-existing health problems or conditions? Evolved resistance or evolved tolerance, a desensitization to the effects of the toxin, can also affect the dose-response relationship. As an example, kind of a sidebar here, I think it's interesting how some species of rabbits have evolved so that they can eat poisonous plants, while other rabbits who have not developed that tolerance are going to be killed by the same plant if they eat that same plant. That's kind of what we're talking about here with evolved resistance or tolerance. This kind of hints at species selectivity as well, which we'll talk about specifically in a subsequent slide. Then finally, environmental conditions can play a role as well. The main point here is it's not just dosage size. There are other things that have to be considered, like those things that we've mentioned on this slide, including temperature, the ambient temperature at the time of the exposure can play a role. Some concepts that we need to be familiar with as safety professionals. These are concepts that we probably won't talk about that much in the workplace when we're doing our day-to-day work as a safety manager. But these are concepts we need to be familiar with. These are concepts that you may see on certification exams. The first concept I want to throw at you, it is covered in Chapter 6. The acronym for this concept is LD50. LD50, or the LD part of the 50, stands for lethal dosage. This is the dosage that will kill 50% of lab animals. Usually measured as milligrams of substance per kilogram of body weight, or it could be micrograms of substance per kilogram of body weight also. Milligrams per kilogram is the most common measurement units used when we're talking about LD50. LC50 refers to airborne concentration of a toxin. And the LC50, lethal concentration 50, is the concentration that will kill 50% of lab animals when they are exposed to the substance in the air, when they are exposed to a substance that the animals would inhale. The units that we'll normally see when it comes to lethal concentration 50, parts per million, parts per billion, milligrams per cubic meter of air, or micrograms per cubic meter of air. And I have the abbreviations for each of these different units in the parentheses. Another concept that's related to LD50 or goes along with LD50 and LC50 is ID50. And I thought it was appropriate to go ahead and throw this in here since we are in the process of coming out of the coronavirus pandemic. ID50 is the infectious dose or infective. You'll see both terms used interchangeably. The infectious or infective dose. It's the number of organisms, or microorganisms to be more precise, number of microorganisms causing infection in 50% of subjects. And microorganisms could be bacteria, could be viruses. Those are going to be most of the microorganisms we're talking about, but there may be others as well. But the infectious dose, number of microorganisms causing infection in 50% of subjects. Now, LD50, LC50 are discussed in Chapter 6. ID50, I don't believe it is discussed in Chapter 6 on industrial toxicology. If you have any questions about either of these concepts, let me know. The value in being aware of these concepts and knowing these concepts, I think primarily is for certification exams. It's not something that you're not going to go into the factory and start talking to workers about LD50 values, because these values are established with laboratory experiments using animals as subjects. Now they can be extrapolated, or findings from this LD50 research can be extrapolated and be part of the basis for human exposure limits. But for the most part, we're talking about animal research that's not directly applicable to the human worker. This chart, I throw this chart up here because it shows that for most substances, subcutaneous exposure will have the greatest effect. What we have in this table, go ahead and draw some lines here to break it up a little bit. We have 3 different substances. We have fluoroacetamide, we have chlordane, and we have endrin. And for each of these substances, we have the LD50 values when the exposure is ingestion or orally, when the exposure is through the skin or dermally, or when the exposure is subcutaneous, an injection into the organism. For fluoroacetamide, the subcutaneous route of exposure, it only takes 250 milligrams per kilogram of body weight for 50% of the lab animals to die at this relatively low level of concentration. Now, dermal exposure, absorption through the skin, it takes a lot more of a concentration. It takes 402 milligrams per kilogram. For oral exposure through ingestion, it takes 371 milligrams per kilogram. And we see also for rats exposed to fluoroacetamide, the subcutaneous route of exposure, it doesn't take as much when that is the route of exposure. And we also see how there's differences for the most part between ingestion and absorption through the skin. Those types of exposure, those routes of exposure also. Now there is something interesting here when we look at endrin. They looked at the LD50 when the exposure occurs orally through ingestion, and when the exposure occurs dermally through absorption through the skin. It's the same concentration. 18 milligrams per kilogram exposure to endrin, absorption through the skin, will kill 50% of lab animals. 18 milligrams per kilogram exposure to endrin when it's ingested will kill 50% of the lab animals that are exposed. Kind of a sidebar, not necessarily related to this, but the issue of species selectivity, maybe not really that applicable for industrial toxicology and safety in the workplace, but I think it's interesting that how some species have evolved a tolerance or a resistance to specific toxins. And a good example of this would be dogs and humans. Dogs, as far as I know, do not have any sensitivity to the chemicals in poison ivy. On the other hand, humans do, for the most part. Not all humans. There are individual differences within humans. Some humans are more sensitive than others, but humans are sensitive to the toxins that are found in the poison ivy plant. And there are other examples as well. I think it would be fun just to explore this further if we had more time, how different species have different degrees of tolerance to different toxins. Now, I kind of hinted at this previously. How do we know what the threshold effect is? How do we know what the LD50 value is? We know this through research. Laboratory experiments where animals are used in the experiments. The animals are exposed to toxins at varying concentrations. Researchers study the effects of the toxins. This study can involve a post-mortem, looking at the organ systems, dissect the exposed subject, look at their different organ systems to see how it was affected. The other type of research that's conducted would be laboratory experiments. Laboratory experiments where you're using non-living biological materials. A term that's used in the textbook, in vitro, in a test tube, is descriptive of this type of laboratory experiment. We're assessing the effect of different toxins on biological materials, but we're using non-living biological materials. For example, we might study the effects of a toxin on tissue samples. Instead of exposing an entire organism to the toxin, we just take a tissue sample and see how the tissue sample reacts to toxin exposure. There are also epidemiological studies where we study humans, living or dead, who have been exposed to different toxins. And when we say have been exposed to different toxins, we're talking about accidental exposures. We're not talking about an intended exposure to see what effect it's going to have. That would be unethical to conduct that kind of research. But there are cases where workers, perhaps in a manufacturing facility, was exposed to a high concentration of ammonia gas. Or, if we think about Chernobyl, the nuclear catastrophe that occurred in 1986, a vast number of humans were exposed to ionizing radiation. Researchers have for years, since 1986, been studying humans who were exposed to the radiation released at Chernobyl back in the 80s. So that's what we're talking about with epidemiological studies. Sometimes we're talking about people who live on beyond their exposure, and we study how the toxin affects their lives, affects their organ systems. Or in some cases, it may be an autopsy of a human being who was killed as a result of their exposure. And what we're looking at, generally speaking, in epidemiological studies are the health effects of exposures at different concentration levels. So, in a nutshell, this is how we know what the different threshold values are. This is how we know what exposure limits are from this type of research. This is how we know what the LD50 values are, or the LC50 values, from this research. And one thing I want to mention, I know some of you, I kind of zip through it pretty quickly here, but I want to talk a little bit more about laboratory experiments with animals. I know for some of you out there, myself included, to some degree, it's morbid to think about using animals in research. One side of me says, "Hey, that's not cool. We shouldn't be using animals to test the effects of different toxins." But then the professional or safety professional side of me understands that it's probably the best method we have available in some instances to really understand the effects of toxins. We can't do this to human beings. We can't expose human beings to the toxins to see how the human body will respond. But again, it may not be completely cool to use animals, but it is our best option for fully understanding the effects of different toxins. A lot of the research that I'm referring to does not specifically focus on exposures in the workplace, but the LD50 values, the LC50 values, the values, the threshold of effect concentrations that have been established, those are taken as a basis for extrapolation to humans in the workplace. They help to provide some general guidelines or recommendations for all humans. We will talk more about work-related exposure limits and perhaps talk a little bit more about the development of these exposure limits in video U2V3, Unit 2, Video 3. Last thing I want to talk about, toxin interaction, mixtures. I would say most of the time when we have chemicals in the workplace, It's not just going to be one chemical element. It's going to be a compound of different chemicals. It's going to be a mixture of different chemicals. We're going to have different chemicals interacting. We're going to have different toxins perhaps interacting. And as these toxins interact, they can increase, decrease, or even eliminate the health effects of toxins. And as safety managers, and especially if you specialize in industrial hygiene, we need to recognize the potential for interactions between different toxins. There are 4 different types of interactions that I want to talk about that are commonly discussed. One of the interactions that we want to talk about is potentiation. Potentiation is when the toxicity of a substance is created or intensified by the presence of other substances. Say we have substance A that is not toxic. By itself, substance A is not a problem. But substance B, which is moderately toxic, is introduced, is mixed with substance A. When this mixing occurs, it causes a non-toxic substance A to become highly toxic and have severe health effects. Substance B is a potentiator for substance A. Now, one common potentiator, that's a potentiator for many substances, is alcohol. Alcohol can interact with a lot of other chemicals, and it can cause the effects of other substances to be intensified. Another effect that we need to consider when there's mixtures between substances is the additive effect. The health effects of one toxin combines with the health effects of other toxins. We have substance A that is moderately toxic, substance B is moderately toxic, and then the combined combination of those two increases the overall toxic effect on the organism. You can think of it in terms of the effects equal the sum of the parts. If toxic A has, or if substance A has a toxicity of 2, B has a toxicity of 2, add those together, we have a toxicity of 4. If we do not have any other information about the interaction between different substances, the general rule of thumb is to consider mixtures to be additive. The general rule of thumb is that the effects of one will add to the effects of the other to increase the overall effect of the mixture. Then we could also have a synergistic effect, and I refer to this also as a multiplier effect. The toxicity of the substances is greater because of the interaction with other substances. Substance A, moderately toxic, substance B is moderately toxic, but when combined, the toxicity of one or both is greatly amplified. It's more of a multiplier effect than an additive effect. The combined effects are greater than the sum of the individual health effects. The whole is greater than the parts. And if we want to use a mathematical equation to illustrate this, 2 plus 2 is not equal to 4. 2 plus 2 is equal to 8 because of this synergistic effect going on between the substances. And one thing I need to mention, these are really simple examples. I'm talking about 2 different substances coming into contact with each other. There could be many more substances than just the 2. There could be 5 or 6 or more interacting, affecting one another. The last type of interaction I want to talk about, or the last effect, is the antagonistic effect. Toxicity is reduced or eliminated when 2 or more substances interact. If substance A is toxic, substance B is not toxic. But when combined, substance A becomes non-toxic. This can be good or bad. If we're talking about medications and this antagonistic effect occurs, you're taking medication A to help you with a specific ailment. But then you take medication B that eliminates the effect of medication A, then that antagonistic effect, I can't talk, the antagonistic effect is not a good thing. Now, in other contexts, it may be good if substance B causes substance A to lose its toxicity. And kind of in effect is what we're talking about here. Same thing that goes on with antidotes to poisons. A poison is ingested or inhaled. Person who is exposed is taken to the emergency room. An antidote is administered. The antidote is going to be another chemical compound or another substance that counteracts the effect of the poison. Antagonistic effect. Now, this is just a really brief, very simple introduction to on chemical mixtures. When you take 4423, Safety Management 4423, the title of that class is Industrial Hygiene Management. It's like Industrial Hygiene Part 2. We will go into much more detail with chemical mixtures in that class, and we will do some calculations related to the mixing of different substances. All right, that's all I really want to say as far as the lecture about industrial toxicology. Again, you could do a whole class just on industrial toxicology. This is just part of our industrial hygiene class, our introduction to industrial hygiene class. In this unit, we've talked about what toxicology is, types of toxins, asphyxiants, acute, chronic toxicity, systemic toxicity, localized toxicity, organ-specific and species-specific toxicity, sensitization, desensitization, dose-response relationship, and toxin interactions.